Hi everyone, this is section 2, chapter 5, magnetism. And section 2, which is the second part. In the previous part, I'll just do a quick review. We talk about the Oersted demonstration, and the Oersted proves that he found that if the current going through the wire, the magnetic field is going to be produced around that wire. It was for a straight wire, current carrying wire. But now we have a magnetic field of the circular coil when the current is going through that coil. As you see over the screen, we have a coil, a wire in one loop. We can call it a coil. In that case, it will produce a magnetic field around it if the current is going through that coil. If you have a wire like this one and you bend it in that way and the current is going in that direction, current is going in that direction, that's the direction of the current, and the current is going throughout all the wire, and then it's going to come out from that side, from that direction. In the previous video, we just explained how to indicate the direction of the magnetic field around the straight wire. We just simply said that direction we can find it by using our right-hand rule, which is our forefinger. We're going for the direction of the magnetic field, which is circulating around the wire, and our thumb is showing us the direction of the magnetic direction of the current. So now, according to that figure that I draw, if my thumb goes to that direction, that's going to be the direction of my thumb. And then if I follow the direction of my thumb, I will just do it like this. In that case, I will see that my forefinger from the outside of the coil, I mean that area, my forefinger, that area, it shows me it is going into the board, into the screen, right? It is going into the screen. So the field is going into the screen and going to continue the circulating around the wire in that direction. Continue the circulating. So inside the coil, it is going to be the out of the board, out of the screen. So if I follow the direction of the current over there, I will see my thumb is showing us that direction. So magnetic field is going to be at that area. The magnetic field is going to be again into the board, into the screen. And when it's into, it means it's going to circulate and then comes out to that direction. So that all inside the coil is going to be into the out of the page or out of the screen. The outside of the coil is going to be into, which we don't need the outside. In that case, we only need the inside one. So always we are going to find the magnetic field direction of it and the magnetic of it in that area, which is the center. So always it might be out or in. We have one example over there. It is clearly explained. We see the current is going to the up, and that's the direction of the current. And that's going to go in that direction. As you see, circular current. So the thumb shows me this direction. That's the direction of my thumb. So my forefinger is telling me in that area, my forefinger from the inner side is going into the screen. So it is all into. When it's circulating from the other side, the direction of the current looks like opposite to that one. So in that case, it's going to be inside again. And from that part, it will be outside. So the field is out from the outside of the coil. And it is inside from the inside of the coil, which we need the center of the coil. At the center of the coil, what is going to be the direction of the magnetic field? It is going to be inside the screen or inside the page, which is, you can say negative Z or positive Z. It was for the direction, guys. Now, for the formula, if you want to find the magnitude of that field, which is going to be produced around the circular coil, we might use that formula, which is mu naught. You already know that, magnetic permeability of free space. 4 pi times 10 to the power negative 7, and it stands for the number of turns. Number of turns. How many loops you have, how many circles you have. And I stand for the current, you already know that. R stand for the radius of the coils, which is the unit of it, it must be meter. And for the number of the coil, it's just a number, we don't have a unit. You know already the unit of the current, and you know the magnetic field. Now it is for the coil. What if you have two loops of the wire and the net magnetic field B net at the center of the two wires is equal to 0? In that case, you're going to say B1 is equal to B2. Like if you have one circle, one loop in that direction, if you have another loop in another color they throw, if you have another coil over there. So if the current in one of them goes to that direction, that's the current 1, that's the current 2. In that case, at the center, we will have one field out, one field in, because two different directions. So B net at the center, the magnitude of it is going to be equal to 0. So it means B1 is equal to B2. So when B1 is equal to B2, we can easily say that N1I1 over R1, it must be equal to N2I2 over R2. We already canceled the mu naughts. It is in the case if the magnetic fields were equal to each other. We have this bizarre question 2016. The strength of the magnetic field in the center of the circular current carrying coil is inversely proportional to the coil numbers. In that case, if you want to answer that question, you should simply just use the formula. We have mu naught N I over 2R. If I increase inversely proportional with the coil numbers, if I increase the coil numbers, keep all of them constant, so the B will goes higher. And inversely proportional with the magnetic permeability, inversely proportional with magnetic permeability of the medium. It means it's inversely proportional with the mu naught. So if I increase the mu naught, B should increase because they are directly proportional. C is going to say that inversely proportional with the coil's radius. Inversely proportional with the coil's radius. Look at this one. If I have more radius, the magnetic field should be less. It should decrease. So C is going to be the correct answer because it's below all of the mu naught and I. If I have a larger radius, it means you have a less magnetic field. Okay, we have a very nice question about that subject, but let's solve the practice 5B and then we're going to go for that question. Practice 5B, if you look at the question, calculate the magnitude of the magnetic field at the center circular coil of the 10 turns, radius 10 centimeter, and the current is 20 amperes. So we have an N, we have a radius, we have a current 20, and we have mu naught already, we know that, which is 4 pi times 10 to the power negative 7. So easily we can go for that question. For that way, B is equal to mu naught Ni over 2 times R. B is equal to 4 pi times 10 to the power negative 7 times 10, the number of turns, times 20 is the current, and over 2 times the radius is 0.10 centimeter. It's 10 centimeter, we're going to make it meter, it will be 0.10 meter. In that case, we just multiplied by 10 to the power negative 2, which is similar to divided by 100. When you calculate it by the calculator, you're going to see B is equal to 1.3 times 10 to the power negative 3 Tesla. That's going to be the magnetic field. And in the question, is not going to ask us to find the direction. Now let's go for the previous question, sample problem question. In that question, we studied 2 formulas. One of them for the straight wire, other one is for the circular loop coil. In this question, we combine them both together. Now let's take a screenshot and then go to the other side, to the empty blank, empty page. Okay, now then let's go ahead. Now, have a look at the question, guys, what it's going to say. A long straight wire carries a current of intensity 6 ampere. So the current is given, where a part of it is bent in a circular coil, circular loop of 1 turn. So it means we have a straight wire and we have a loop, as you see in the question. Straight wire, and then the part of it is bent into the circular loop. So in that case, we should just take care about the 2 formulas that we studied. Okay, and the question is going to say that the radius of the turn, the radius of the coil is 0.04 meter, as shown in the figure. So the figure should give you, calculate the magnitude, why the figure should be given. Calculate the magnitude and the direction of the field. If the question asks you for the direction of the magnetic field, it should give you the figure. But if it does not ask you for the direction, does not need the figure. Okay, so now let's draw the figure. In the figure, we have a straight wire, and the part of that straight wire is bent into the circular coil, and then it's going to go over there. So that's going to be the direction of the current. That's going to be the direction of the current. As you see, it is all going throughout the wire, and then it's going to go up on the way out. That's going to be the direction of the current. So this is the current of the wire, and we're going to have over there same current, but we will name it as a current of the coil. And we have a point from the center, which we call it the radius, that point. So that distance is equal to the distance or the radius, same thing, 0.04 meter, which is equal to the radius, same thing. Okay, now for calculating the magnitude, I have to find 2 B's. B for the coil and B for the wire. And then at the end, we have to find a B net. Sorry. Okay, so for the B coil, what was the formula? Mu naught Ni over 2R. So mu naught is 4 pi times 10 to the power -7. Because it's 1 loop, as you see, we're just going to use 1 for the number of turns. For the current, we're going to use the 6 because the same amount of the current is going through the straight wire and through the coil. And over 2 times 0.04. The result is going to be 9.4 times 10 to the power -5 Tesla, if I am not mistaken. For the wire, we're just going to say mu naught I over 2 pi distance, which is 4 pi times 10 to the power -7 times the current is 6 over 2 pi times 0.04. You're going to cancel pi with pi, and this one is 2. And then you're going to have 3 times 10 to the power -5 Tesla. Okay, this is going to be the result. That's the magnitude, but we have to know the direction. And I have to say that B coil, B wire. So, am I supposed to add it or minus it? I will follow the direction. In that case, we need the direction. Guys, look, if we look at the question, if we want to have a direction of the straight wire, what we should do? For the straight wire, we said we're going to use our right-hand rule, and the forefinger is going to show us the magnetic field. So now this is direction of the current, direction of the magnetic field. If I just align my thumb according to that arrow, in that case, I will see my forefinger. It's going to show me the into the page. So B wire is into, so it means -Z, right? And if I align my fingers, my thumb, according to that direction of the current, that's direction of the current. So I will see that my forefinger outside of the coil, it shows me into, but inside of the coil is going to show me out of the page. So the B coil, it's going to be out, and it might be positive Z. So now I can write this one positive Z, and that one I can write negative Z. So now that's why I subtract them, I minus them. So the result is going to be equal to 9.4 minus 3, it's going to be 6.4 times 10 to the power negative 5 Tesla, and the direction of the bigger one, which is the positive Z, and the result is positive. So in that question, if it does not give you the direction, it does not, if it's not going to ask you for a find direction, you don't need to have a figure. You're just going to find the magnitude and then minus them. Never ever, you cannot add them in that kind of question, because you have a loop and a straight wire, always the magnetic field of these two will be opposite. So, but you have to know that for the direction, you have to know that which one is in, which one is out. I hope you understand that question. And as you see, we wrote direction is outside of the page, which is positive Z. Now we have that question. It's similar to the other question, similar to that previous question. Electric current travels one loop in a circular coil of diameter 50 centimeter. Diameter, it's given, we have to make it the radius. That's why we wrote 25 centimeter, and then we have to change 25 centimeter to meter divided by 100, which is going to be 0.25 meter. Calculate the intensity of the current if the magnitude of the magnetic field at the center of the coil is 2 pi times 10 to the power negative 5 Tesla. So now we have a field. We just need to find the amount of the current. Mu naught Ni over 2R. B is equal to 2 pi times 10 to the power negative 5. Mu naught is 4 pi times 10 to the power negative 7 times the number of the turns is not going to, it's going to be 1, it's mentioned, 1 loop, times the current, which is a noun, and divided by 2 times 0.25, sorry. Now I can cancel 2 pi, 4 all together, because 2 times 2 times 2, it's going to be 4, and 4 with the 4, they will cancel each other out, and the pi will be cancelled by the pi. So now it could be, the result is going to be equal to, as you see, it's written over there, 25 ampere. That's the result, or that's the direction of the, and that's the value of the current which is going through that coil. Okay, let's go ahead with the one question from the chapter review. And that question also, we're going to go to the next slide, to the next page, and then we're going to solve it over there. It is the chapter review, question 26 from chapter 5. Okay, here is the question. Guys, in the question it said that 2 circular coils are concentrated and lie in the same plane. It means you have 2 coils, they are inside of each other. The inner coil contains how many turns? 120 turns. So let's name it as N1, 120 turns. Okay. And the radius R1 is equal to 0.012 meter. And the current one, I1, is equal to 6 ampere. But the outer coil contains how many turns? 150. N1, N2 is equal to 150 turns. And R2 is equal to 0.0, as you see, it's given 0.017 meter. And I2 is unknown, we need to find I2, but in the question we have a note, which is the note is going to say that the net magnetic field at the common center of the two coils is 0. So B net at the center is equal to 0. When the question said B net is equal to 0, it means B1 is similar to equal to B2. So what is the formula of finding B1? Mu naught N1 I1 over 2R1 equal to mu naught N1 N2 I2 over 2R2. Now, you know that they will be canceling each other, the mu naught with the mu naught, 2 with the 2, only what is going to remain? N1 I1 R1 equal to N2 I2 R2 will remain. And we have them all. N1 is equal to 120 times I1 is equal to 6 over 0.012 equal to I2, N2, sorry, it's equal to 150 times the current, which is a noun, and over 0.017. So now you can just use the calculator and find out the I2, it's equal to 6.28 or 28 something amperes, if I'm not mistaken. So it's a bit higher than this one. Now, what must be the magnitude and direction? We found the magnitude. Okay, we found the magnitude. Directions, you can simply just say that opposite of the I1. Of I1. Why? Because we already know that if you have a coil current going in that direction, in that case, the field, direction of the magnetic field is out. You know that that's the direction of the current, that's the direction of the B. If it is the inner one. The outer one, we can have a coil and we can have a direction of the current, which is opposite to that one. Should be opposite to that one, sorry. It should be in that direction, which is opposite. That's going to be the I2, outer one. That's going to be I1, inner one. So the magnetic field in that one is going to be into the page. That's a B2, that's a B1. So in and out, they cancel each other out. In that case, you could have a net magnetic field equal to 0. So only you should say the direction of the two coils, current in the two coils must be must be opposite of each other. Sorry, it's not 6.28, it's just only 6.8 amperes. Okay.